Hi everyone, welcome to the second part of the Slide 3 webinar series, which is about seepage and support analysis. My name is Sina Javan Khoshtel. I'm a geomechanics specialist at Rocscience, and also I'm responsible for 3D expert modeling at the company. We are Rocscience, the world leader of developing 2D and 3D software packages for civil, mining, and geotechnical engineers. For over 20 years, we have built geotechnical tools used by over 8,000 users around the world. We have more than 50 employees now at our head office in Toronto, and more than half of them, they hold advanced degrees in engineering. As you may know, this is the second part of the three-part webinar series of Slide 3. In the previous webinar, I talked about how to create the geometry, 3D geometry, to do the 3D slope stability analysis. As part of the 3D slope stability analysis, we need to do the seepage analysis and support analysis as well, which I'm going to talk about them today. And our next webinar, which is going to be on March 5th, it's going to be about probabilistic analysis for 3D slope stability. Supports, loading, and groundwater are the features that we have in the Slide 3 software that I'm going to talk about them one by one. And I'm going to explain how to use these features with several examples today. Let's start with the support analysis. Before I start, I continue the presentation. If you can't hear me, please write down the chat section or a question section. And at any time during the webinar, if you have any question, just type down your question, and we're gonna answer your question right away. So feel free to ask any question that you have. Let's start with support analysis. The support library that we have in the Slide 3 software is similar to the Slide 2 software, including end-anchored, geotextile, grouted tieback with friction, micropile, soil nail, and user-defined. Support can be applied at any 3D orientation or location by different options that we have in the software. Before I explain the different support types that we have, let's look at the basics of the limit equilibrium, how it handles the support. In the limit equilibrium analysis, support must intersect a slip surface to have effect on the factor of safety. For example, the left figure, there is no intersection between the support and the critical slip surface, so it doesn't have the support doesn't have any effect on the factor of safety. However, in the right figure, there is an intersection and the support force will be applied to the factor of safety calculations. The supports in the limit equilibrium analysis, normally they improve the stability in two ways: direct resistance to sliding or modifying normal stress on the sliding surface. The relative contribution of the supports depend on the orientation of the support, type of support, depth of sliding, and frictional resistance of soil. If we look at, this is the 2D view, the orientation of the applied support force depends on the type of support that we use. So we can have different orientations for the support. Depends on the type of support. For example, end anchored support or grouted tieback or soil nail, the force is usually applied parallel to the direction of the support, similar to here. This is the support. But for geotextile or user-defined, we have different options. The support can be tangent to the slip surface, similar to here, parallel to support, or bisector tangent or parallel angles. For user-defined case, you can define your user-defined angles as well. When support intersects a slip surface, a force is applied at the point of intersection of the slip surface with the support. And the magnitude of the applied force is used to determine a force diagram, like these two force diagrams. And a force diagram simply represents the maximum available force which the support can apply to the sliding mass. Depends on the type of support. For example, for end anchor and micropile, this is constant force that is applied to the intersection point of the support and the critical slip surface. However, for geotextile, grouted tieback or soil nail, depends on the mode of failure. This application, this force diagram can be different, and the value is going to be selected from this force diagram depends on the type of failure that we have, mode of failure that we have. For example, for geotextile, we only have tensile and pull-out. But for grouted tieback or soil nail, we may have a stripping as well. Stripping is the type of failure that the slope fails, but the support stays embedded in the slope. For the user-defined support, the force diagram is directly defined by the user that I'm going to explain it later. Okay, let's start with the end anchored in our support types. For the end anchored, you should define the anchor capacity, which is the maximum load that the anchor can sustain. End anchor supports can be used for different support systems, such as mechanically end anchored rock bolts or deadman anchors. Geotextile is another type of support that we have in the Slide3 software, which represents a group of geosynthetics such as geogrids, geofabrics, or geotextiles themselves. We have a parameter in geotextile support type called strip coverage. And normally, this type of reinforcement is placed in strips of a certain width in the soil geometry, in the soil profile. And the strip coverage refers to the spacing between these strips. If there is no spacing between two adjacent strips, the strip coverage would be 100%. But if there is any spacing similar to here, the strip coverage is going to be calculated using this equation, and it's going to be less than 100%. Because of the flexible nature of a geotextile type of reinforcement, the orientation of the support, the orientation of the force which is applied to the slip surface is not always assumed to be parallel to the support. So it's not always like this. It can be tangent or bisector. And it depends on the displacement of the failure that we have. This support behaves differently in terms of orientation. In the M+ version of the Slide3 software, we added common types of geotextile, including the Tensor International. As you can see, we have different types, or McAfee manufacturer. And for any of these types that you select, you can have different information based on what the manufacturer provides. For example, you can look at the ultimate tensile strength, and you can look at all these reduction factors for the strengths of the geosynthetic reinforcement. Grouted tieback support is another type of support. It has a bonded length, which can be defined as a percentage of the length of the support or the length itself. The tensile capacity is the maximum capacity that the support can have. We also have plate capacity, which is the maximum load that the plate that connects the grouted tieback to a slope can sustain. For the grouted tieback, we have this force diagram, and you can compute different types of failure mechanism: pull-out, tensile, and stripping. In this case, that you can see here, stripping depends on the plate capacity. So the capacity of the plate is less than the tensile capacity, so you can have a stripping. But sometimes, if the plate capacity is higher than tensile capacity, you cannot have this stripping mode of failure for this support type. The grouted tieback itself does not account for friction between the bonded lengths and the frictional soil. But we have another option, grouted tieback with friction, which accounts for frictional strengths of soil grout interface. The next one is micropile, can be used to model piles and micropiles. It's a little bit different from other support types in the Slide3 software. The resistance to movement in this support is provided by loading transfers to the support direction. If you can see here, this is the direction, is the load is transfers to the support direction. Compared to the other ones that the load is force of the support is parallel to the support direction. Another one is soil nail support. You can use it to model soil nails. It's the bonded length is 100%, so it's bonded along the entire length. So it's equivalent to the grouted tieback with the bond of 100%. User-defined support, you can define your force diagram here by putting the numbers of distance and capacity. Sometimes whatever I showed so far is the support force diagram is either constant or linear. But sometimes, for example, if you model a support in the RSPile software, you get the force diagram which is non-linear. You can export that from the RSPile software and import it into the Slide3 software. As you may know, the RSPile software and Slide2 software, they have integration. It means that you can define the supports in the Slide2 software. You can define piles and use the RSPile software to do the analysis and bring back the results. We don't have the direct integration here from Slide3 to RSPile, but you can easily model your piles in the RSPile software, and as I said, export the force diagram and import it here using this import option. As you may notice, we have an option in the support section for each support type, which is called force application. We have two different options of active and passive. Let's see what these options are. In general, the equation for the factor of safety is the relationship between the resisting force, ratio of the resisting force over driving forces. So our resisting force is shear strength, the driving force is shear stress. The support type that we have, the support force, can act in two different directions. It can either reduce the active force or driving force, or increase the passive force or resisting force. For example, if you look at the equation here, if we have a support and the support is reducing the driving force in the factor of safety equation, this support is called active. But you can add support to increase the shear strength or resisting force. This support is called passive. Depends on the support type. If the support exerts force on a sliding mass before the movement, for example, like grouted tieback or end anchored bolts, the support is going to be active. But for soil layers or geotextiles, as long as we don't have any displacement, there won't be any force from the support. That case, the support is going to be passive. For loading, we have different types of loading in the Slide3 software, including point loads, distributed loads. We have uniform and non-uniform distributed loads, and we have seismic loads. Loads can be applied at any 3D orientation or location by different options that we have in the Slide3 software. Okay. Let's start the examples for support. We have two examples for the support: retaining wall, geosynthetic retaining wall, and a landslide. For the geosynthetic retaining wall, we're going to import a model from a Slide2 that we define the reinforcement in the Slide2 software. We're going to compute and look at the results. Then I'm going to remove the geosynthetic reinforcements, and I'm going to add a new pattern, like a bolt pattern for the reinforcement, and compute again. Okay, let's first look at our example in 2D. We use different patterns. This is the retaining wall. We use 3 different patterns. If I look at the properties of supports, we can see that it's geotextile with a strip coverage of 100% and tensile strength of 7.3. We use different types. We have 3 different material regions. We have abutments here. We have the reinforced zone, backfill, and foundation. If we look at the results, to see how much is the factor of safety. The factor of safety for the 2D case with the Spencer method is 1.5, which is used for design purposes. Yambu gives 1.3, which is always Yambu gives the lower bound for the factor of safety. And if you look at the critical slip surface, you can say it goes behind the reinforced zone because reinforcement elements are strong enough to push the the critical slip surface behind the reinforced zone. What I'm gonna do, I'm gonna show you how to create a 3D model. As I explained in the first webinar, there is a very good integration between our software packages, Slide2 RS2, Slide3 and Slide3 and RS3, and RS2 and RS3, different types of integrations. So it's very easy to go from one software to the other one. Now what I do, I drag and drop a Slide2 model into the Slide3 software, and it just needs one more information, which is the extrusion depth. And if I click on OK, it says it's successful and the model is created in 3D. So very fast and very simple. If I go to the support tab, you can see that these are the 3 different types of geosynthetic reinforcements that I use in the 2D model. If we look at the project setting, you can see that all the options are similar to the 2D one. So Yambu and Spencer, and the search method, you probably noticed that we use the non-circular search method, which is cuckoo search with surface altering optimization. To look at the results, I ran this model before. So here are the results, and there is a critical factor of safety for the 3D case. For the Yambu method, it gives factor of safety of about 1.5 and Spencer 1.74, and this is the critical slip surface. Let's look at the ones that is very similar to the 2D one. You can see that this is the 2D critical slip surface, and it seems that the failure surface goes beyond the reinforced zone. But if you look at the 3D critical slip surface, you can see that there is no way that the critical slip surface goes beyond the reinforced zone. This is the actual behavior of the failure, not the 2D one. And because of the reinforcement intersection with the critical slip surface, factor of safety in the 3D case is about 10% larger than the 2D case. And if we look at the forces that we have, for example, this is a contour for the critical slip surface. And if we look at the normal forces, for example, you can see that at these 2 corners, when we have the intersection of the critical slip surface and the reinforcement material, we have higher normal force, which, as I explained, if you have intersection, the force of the reinforcement is going to be applied to the critical slip surface. So this is the influence of the 3D modeling. What I'm gonna do, I'm gonna go back to this model and I'm gonna remove all the geosynthetic reinforcement that we add. So there is no reinforcement in this model. There are different ways of adding reinforcement. I'm gonna practice another one here, which is applying the reinforcements or bolts to the face or surface. So for example, if this is the face of the reinforcements, if we go to the support tab, we have an option called add support to surface. So I'm gonna click on it. We can define a support type. Let's say it's end anchored. It's fine. we can define single bolt or bolt pattern. I'm going to define the bolt pattern. The length of the geosynthetic ones was 8.8. I use the same length, and to add the bolt pattern, you just need 2 points. One to start, you can either put the coordinates here or select one point on the model and one to the end. You can see that this is the path or direction that the software is going to use to add supports. You can define the secondary path as well. Let's look at the first, a primary one. You can click on preview button. You have primary spacing and secondary spacing. So you have defined the spacing which are equal here. If you are satisfied with the reinforcements, you can click on add, and the software is going to add the reinforcement layers, and click on done. So I removed the geosynthetic ones. I added another type of reinforcement. Let's look at the results for this case. If we go to the support section, you can see that these are the bolts that I defined, and for the results, factor of safety is very similar to the geosynthetic one, which is 1.72. For the geosynthetic was 1.74. The software has an option that you can look at the forces of the reinforcement, or you can look at the base column force. So it is color coded, and you can see the type of failure that we have and the magnitude of the load that the support applies to the critical slip surface. If you look at this one, they are all 100, which we define as the tensile strength, and the failure type is tensile for this example. So this is another option that we have. Okay, let's move on to the next example. Our next example is a landslide. I created this geometry in the previous webinar. It's a landslide, but in the previous webinar, we didn't have any load and we didn't have any support. So for this model, I'm gonna use the previous geometry. I'm gonna add the load. We look at the results with the load, and then I'm gonna add the support at the region that we have the critical slip surface, and then compute again and look at the results. Okay, so let's open the initial model for this example. So this is the initial geometry that we had. We have 3 different layers, and we have 4 boreholes to define the layering of the material. For this one, let's say this is a landslide, and we have a road on top of this landslide. So to apply the load for that road, I'm gonna go to the support and load section, and I'm gonna go to add loads. Let's say the width of the load is 230 and the height is 10 and the magnitude is 40. The load is created here. You can change the location, move it up a little bit, rotate it, and move it to the top. Let's say this is our load, and you can apply it to the train or to a specific volume, horizontal plane elevation, or arbitrary oriented plane. So I'm gonna project it to train. When I hit OK, the load is created on top of this landslide, and it gets the shape of the train as well. So we ran this one before. This is the critical slip surface for this case. Factor of safety is 0.9. Here is very interesting. First of all, if you look at the shape of the critical slip surface, it is extending along the load. So the way that we define the load, it extended the critical slip surface. And if we look at the, let's say, base normal force, you can, and if we zoom in, you can see that the base normal force along the load is higher. So the maximum happens where the load is. So what I'm gonna do for this model, I'm gonna add support around the region that we have the failure. So I showed you one way of adding support. This is another way. So if we go to support, we have an option called add support. So it's different from the other one that we add a pattern. Let's say this 70 by 70, and for the length is 10 meters, the horizontal spacing is 3, vertical is 2, and we can define the trend and plunge, let's say with 15 degrees for the trend. For the support type, it is soil nail, and the capacities, they are all the default values. So if I move my support to this region and rotate it a little bit, let's say like that, and move it a little bit, which covers the critical failure surface that we have. So if we look at our support, you can see that this is the support with the 15 degrees angle, and it is around that region. So to see what happens, I ran this one again. I computed the results before, and here are the results. A factor of safety jumped to 1.1. And if we look at the critical slip surface, it is a little bit different from the case with no support. The other thing is you have the option in the Slide3 software to look at the supports that they have intersection with the critical slip surface. So the ones that it's showing now is actually the ones that they have intersection with the critical slip surface. And if we look at, you can look at the force diagram for the supports. Let me click here. These are the force diagrams for each support that you can look at them, or again, you can look at the bolt column force. This one is a little bit different. It is soil nail, and we have pull out, stripping, and tensile. We don't have any stripping because tensile plate capacity is similar to tensile capacity. So the type of failure that we have here, they are tensile, the red ones, and the pull-out capacity, which is changing, depends on the material parameters. So this is the landslide model. Okay, let's move on. Let's talk about the groundwater analysis in the Slide3 software. There are different methods of defining groundwater in the Slide3 software. If you want to define a water table, you can use the borehole manager. You can use import any surface to assign it as your water table, or you can define your pore pressure using location or pressure grids. If you want to do a more advanced finite element analysis, you can run it in the RS3 software and then import the results as grid into the Slide3 software. If you look at the project settings, we have different options of adding water surface, RU coefficient, and water grids that I'm going to explain one by one. Water surface I explained before. About the RU method is a very popular and simple method. If you select this method, RU coefficient can be specified in order to define your pore water pressure. What happens is the RU coefficient simply models the pore pressure as a fraction of the vertical earth pressure for each column in the sliding mass. So you can see this is the vertical subsurface soil stress, and you define a coefficient between 0 to 1 and find the pore water pressure. The advantage is very easy to implement, but the disadvantage is it's difficult to assign different RU values to different materials. If we define RU method for pore water pressure analysis, that's the only method that we can use for pore water pressure. You cannot use other methods. And if you have a material that has different RU at different locations, you have to define different two materials instead of one material. and it can be combined with water, surface, and grid options for different materials as well. The grid method, if we select this method, you can assign a water grid, including total head, pressure head, or pore pressure to calculate the pore pressure for the material. From the data at any grid point, the pore pressure at any point is going to be calculated by interpolating the pore pressure between different grid points. The advantage of this grid option is that you can do the seepage analysis in the RS3 as I explained before and import the data into the Slide3 software, which I'm going to show you in a couple of examples. For this section, we have 3 examples. One is the landslide example, a little bit different. The second one is a dam example, and the last one is a levee with relief wells. And I'm going to explain every example in details, and I'm trying to explain all the features that we have related to the groundwater analysis. Okay, the first example is very simple. I just want to show you 2 different ways of creating water table. So basically, this is from the previous webinar. I defined the water table using the borehole manager. What I'm going to do, I'm going to copy the surface that is created using the borehole manager, and then remove the water table from the borehole manager, and then assign the water table to the copied surface. So to show you how to use the surface or to use the borehole. Okay, let's open the third example. This is the final model from the previous webinar. So factor of safety is 0.833. This is the water table created using the borehole data. So if we look at here, this is the surface that is created using the borehole data. What I'm going to do, I'm going to copy this and change the role to construction. So in case that it doesn't have any effect on our results. Next, we go to the borehole manager. Let's look at our borehole manager. You can see that the water is defined using the elevation option. So elevation of 192 is here for each borehole, and the software uses this information to create a surface for water table, the one that I copied. What I'm going to do, I'm going to change all of them to dry. And when I hit OK, the software is going to remove all the boundary condition and material layers, and it's going to create 2 new layers for the material boundaries. So to cut the external volume and create regions of materials, we use the divide all geometry. I explained it a lot in the previous webinar. So the software is gonna use these 2 surfaces to cut our external geometry into different material properties. So the software used the borehole surfaces. And this surface that we copied, this is our water table surface. We go to groundwater, add water surface, and it recognizes this surface as the water surface. When we hit OK, it's gonna ask you if you want to assign this water table to your material layers. Say yes and hit OK. Now everything is ready for computation. So let's say this, instead of copying this surface, I had this surface in advance and I imported it, and I could easily assign it as a water table. And if you look at the results, factor of safety should be, and it is exactly the same as the borehole case because they have the same water table. And if you look at the pore pressure, for example, at the base of the critical slip surface, you can see that it touches this water surface. The rest is dry. Here we have the pore pressure. Okay, let's go to more complicated examples. We have 2 examples. Both of these examples, the geometries, they were created in our RS3 webinar, which we had in the fall. If you want to have access to the videos of these webinars, the Slide3 webinars, and also RS3 webinars, you can sign up in our website, and you will receive the videos. In the RS3 webinar, what we did a steady state seepage analysis for this dam. This is the water table behind the dam, and we did a steady state seepage analysis. But for this case, today I'm gonna do the transient seepage analysis to change the water table level in time in like 6 days. And then for the steady state case and for the transient case after 6 days, I'm gonna import the results to the Slide3 software, and we can compare the results to see what's gonna happen. So if we go to the RS3 case, this is the geometry that we created in the RS3 software. If I want to explain how we do the seepage analysis briefly, because I've explained in the RS3 webinar, for seepage analysis, we have to define boundary conditions for groundwater. So we have 3 different boundary conditions for the this example. One is seepage phase, which is the phase that the water cannot go above that. We have the steady state total head, which is 240, which is the initial elevation of the water table. And also, if we go to the next stage, we have transient water table, because the water table is the total head at this location is gonna change during time, so we have to define the transient boundary condition as well. So to do so, we go to project setting first, change the groundwater analysis to transient, and when you change it to transient, you have to define different stages. You can see 2, 4, 6 days after the initial steady stage case that we have. Also, when you define the boundary conditions, this total head is the initial one, 240, and then you have to define the transient total head as well, which is 2 days, 4 days, and 6 days. So after each stage, we reduce the elevation of the water behind the dam about 10 meters. And let's look at the results and see what happens. Okay, let's look at the first stage. What we're gonna look at is total head. So we define the total head of 240 as the boundary condition here. So you can see that it's red, 240, and it's in a steady state condition. So there is no time, no reducing the elevation of the water table. But after 2 days, we reduce the elevation of the water table, and you can see that here we have less total head, but the total head at this region increases. The reason for that, I'm going to show you the pore pressure as well, but to explain this one, when we reduce the elevation of the water table, we have to give the model some time to dissipate the excess pore water pressure that is created due to a reducing or drawdown of the water table. But we only had 2 days, so pore pressure here is still high. And if we go to 4 days, because we again reduce another 10 meter of the water table, you can see we have 246, a little bit higher pore pressure here, and again another 10 meter reduce and higher total head here. Let's look at the pore pressure and see what happens to the total pore pressure. Actually, this one. To look at the total pore water pressure, what I'm gonna do, I'm gonna look at, I'm gonna hide everything and just look at one contour that we have. So stage 1 is a steady state. You can see that the pore pressure here goes into the dam and goes down here. But right after the drop in the elevation of the ponded water, you can see that there is a bump created here in the model. This bump is the excess pore pressure that is caused by the by lowering the water table, and still exists to the last stage. So what I'm gonna do, what we can do, we can export the pore pressure results from the steady state case, and also the transient case, the last one, which has the highest pore pressure, and to see this lowering the elevation of the water table and also increasing the pore water pressure, what is the influence on the factor of safety. So the first case is the case that we have the water table at the elevation of 240, and the factor of safety using GLE method is 1.34. If we look at the pore pressure, you can see that this is the pore pressure around 246 for the critical slip surface. This is the grid that I imported from RS3. If we go to the groundwater at water pressure grid, you can import it, and these are X, Y, Z, and pore pressure imported from RS3 software. And if we look at the safety map, which shows the map of the model, the weak region is here. This is the case that we have elevation of the water table at 240 and for a steady state. But for the transient case, first of all, factor of safety dropped to 0.7 from 1.34. The reason for that is I also brought the case, the other water table. First of all, the ponded water helps increasing the factor of safety, and we reduce the elevation of the ponded water from 240 to 210. That's the first difference. The second difference is if we look at the pore pressure of along the critical slip surface, you can see this is 313. The other one was for the case with higher factor of safety was 246. So we have higher pore pressure as we saw in the RS3 model, and we have lower water table elevation. So these gonna reduce the factor of safety a lot. Okay, if we go back to the presentation, the next example is gonna be the levee with relief wells. The model, as I mentioned, was created in the RS3 webinar 2. We did the seepage analysis. Webinar 3, we did the slope stability analysis. To explain the model briefly, we have a levee here. This is our retaining wall. This is a water table with the elevation head of 115. We define relief wells to reduce the total head to 106.5 and to see what is the effect of these relief wells. If we look at the 2D model, the ones with the without the relief wells, you can see that the pore pressure here is high. This is the elevation of water table. When we add the relief wells, the pore pressure goes, the total head goes down, and also the level of water table goes down. This purple one is the water table. And if you compare the factors of safeties, you can see that using finite element or limit equilibrium, it doesn't matter, they give the same answer. Factor of safety is 1.2 for the case with no relief wells, and when we have these relief wells, factor of safety goes up to 1.6. Again, the same using limit equilibrium or finite element method. The red failure surface is limit equilibrium. But the problem is in 2D, when you define these relief wells, it is assumed that it is continuous, normal to the plane of the 2D model, so it's extruded. But in real 3D model, you can define these relief wells at different spacings. For example, in this model, what we're gonna do, we're gonna create a geometry, define the relief wells at the steps at the distance of 50 feet to see what happens. So we do the seepage analysis in the RS3 software, and then we bring the results to the Slide3 software. Okay, let's look at the RS3 software. We have a new option in the RS3 software called Wick Drain or Relief Wells / Wick Drain. If I show you the dialog, you can define, this is the spacing of the relief wells, which is 50 feet, and this is the X value. So we define different relief wells with the spacing of 50, and you can define different stages. And we have two types of Wick Drain and relief well as well. Groundwater boundary conditions, we have a total head for the water. If I show you, it's 115. We have a seepage phase, which is here. So these are our boundary conditions. If we look at the results, let's look at the total head and see what happens if we add these relief wells and what is their effect on our total head. So if I hide our geometry, we have contour planes. We define two contour planes, and if we look at the total head in our model, you can see that along these lines, which we define our relief wells, or this view is better, the total head is 106, which is the total head that we define for our relief wells. And we also have ISO surfaces. We define ISO surfaces for total pressure, pore water pressure of 0, which shows the water table. I want to show you the water table in this model as well, which is this one. So if we increase the transparency, this is our water table as well. If we look at the factor of safety calculated using the RS3 software is 1.54. To look at the factor of safety, we can either look at the maximum shear strain, which shows the critical slip surface like this, or you can look at the total displacement. This is our critical slip surface. So again, you can go to File, Export Pore Pressure to a Slide3, and then import the pore pressure to the Slide3 software as well. So if we look at the Slide3 first, this is the Slide3 model. In the Slide3 model, we imported the pore pressure as grid, like this. And also we defined the water table similar to the ones that we had in the model. If we want to look at the results, factor of safety using GLE method is 1.53, very similar to the factor of safety that we have in the RS3 software, or Spencer, it gives factor of safety of 1.56. We can look at the pore pressure for the critical slip surface as well, and you can see that this is showing the pore pressure. You can also look at different parameters like base cohesion, which shows that it's passing two materials. Also, there is another option I explained in the previous webinar. You can look at the column data. So you can look at here your material info, your critical slip surfaces in two materials. And you can look at different parameters, including pore pressure. This material, this one has pore pressure, base cohesion, and other types of information. And also finally, this is the safety map. This shows that this is the unsafe zone for this example. Okay, let's go back to our presentation. So what we showed in the Seepage analysis using the RS3 software, we define the relief, sorry, we define these relief wells, and you can see that the total head is reducing here, and this is the total displacement for the model. Also, you can look at the maximum shear strain as I explained, and this is the ISO surface for the maximum shear strain. So this is where the failure happens, and this is exactly the same as a slide 3. The results are matching. I explained this in the previous webinar as well. As long as you use correct method of analysis, which we have in the slide 3 software, for more than 90% of the cases, you should get exactly the same answer as the finite element method. So the concept of limit equilibrium being circular Bishop method is not true anymore, and we have much more better failure surface searches and different methods to find and match the results of the finite element analysis. Our next webinar is gonna be about the new feature that we have in the Slide3 software, which is the probabilistic analysis for 3D slope stability analysis on March 5th, 2020. To watch the video of these webinars again, please sign up on Rocscience website. You can watch the RS3 webinars and Slide3 webinars that were finished. Thank you for attending this webinar. Please feel free to email us or follow us on LinkedIn, Twitter, and Facebook. Thank you.